Hello, and I hope you're enjoying this warm spring day. Hi, I'm your host, Jeff Williams. We're here on the 16th of June, 2017 for North Star Oasis. We're here for another episode of the Fastest Hour on Television. Thank you for joining us. And in case you're joining us on a repeated basis, we want to remind you that our previous episodes are available on Facebook. Please go to Facebook and like our page, facebook.com/NorthStarOasis. And if you are a first-time viewer, you can always go and check out some of our back episodes, youtube.com/NorthStarOasis. A couple of months ago, actually during the frigid part of the winter, I believe this was January, Congresswoman Betty McCollum had a town hall meeting talking about climate change. So we're going to go right to a clip of Congresswoman Betty McCollum talking about her position on climate change.
So first, I want in full disclosure, here's my position on climate change. Climate change is real. We're major contributors, and I'm against apathy on this because we need to deal with what is happening with climate change now. We need to act now. And in a few minutes, you're going to hear from our distinguished scientists about how climate change is already impacting us and why it's urgent to keep acting and address this threat and to protect our planet from its very worst impacts. But before, I want to give you an overview on where I think we are on the fight against climate change. Last year, the Paris Climate Agreement went into effect. Under the leadership of the United States, President Obama was critical in bringing 194 countries together on this historic agreement, including major greenhouse house emitters like China and India. Now, I'll be the first to tell you, and many of you will agree with me, that the Paris Agreement is not perfect. It was not intended to be a silver bullet to reverse climate change, but rather this agreement was a realistic and absolutely necessary step towards fending off the most devastating effects of climate change by limiting the increase of global temperatures to 2 degrees Celsius. The Paris Agreement, I believe, is vital to progress because it outlines clear objectives and it's a structure for a broader international cooperation to slow climate change and to mitigate its impacts over the decades to come. Now, I believe I know President Trump's position pretty well. His position is also shared by his fellow Republicans in Congress, and it's also their work, they stated it, to hinder or fully cancel the U.S. obligation in the agreement. They've already taken 2 steps to do that by eliminating 2 of the State Department's top programs on climate change prevention. Now, it's beyond their ability to immediately pull out of the Paris Agreement. Mr. Trump and congressional Republicans no doubt will cut the funding in U.S. commitments to the Green Climate Fund, as well as work to keep the tax incentives that are alive and well for the coal industry, and failure to invest in renewable energy with the same kind of zeal. President Trump says he wants to tear up the Clean Power Plan.
So that is Betty McCollum's position on climate change. Here's the thing. If she watched last week's show, hint, watch last week's show, we've explained in very good detail why the Paris Climate Accord was a bad deal. She mentions it's not perfect. We heard that about Obamacare, didn't we? That it's not perfect, that it needs changes. Did anybody in Congress ever think about pushing through the perfect bill? I mean, wouldn't you think if they're going to go all out, go all the way? Give us a perfect bill. Give us a perfect accord. It can be done. But yet, what happens is she, praises Barack Obama for bringing 194 countries together for something that had absolutely no teeth, was essentially a gentleman's agreement, and there was no enforcement mechanism. And living up to the standards set for the United States would punish the average worker in the United States, while China and India and the other BRIC nations would not have to even enforce anything on there. We covered a lot of that last week. But I wanted you to hear from Congresswoman Betty McCollum herself, her position on climate change. And all this talk about we need to battle climate change. I really do think we have other battles that we need to fight. You know, at least I will have to say, as much as I disagreed with his policies, Lyndon Baines Johnson didn't fight a war against the weather. He tried fighting a war on poverty. At least he was trying to do something that would benefit people, not this mythical creature that we have to keep pouring trillions of American taxpayer dollars down a hole that does absolutely nothing for the results. But that's kind of the modern era of what Congresswoman McCollum wants to do. We've got a big sinkhole in the ocean. It actually sucks up carbon. And that's kind of where our money is going, right down that sinkhole. So let's talk about CO2 today. That's really why I wanted to bring Congresswoman McCollum's statement up. We're going to look at a few other things with her climate change town hall from January. But I wanted to make sure we actually take a look a little bit more at the science and understand the different cycles that we go through. Because there's really, I think, kind of like two things that are really not mentioned in the global warming climate change debate. And I really want to highlight them today. So we're going to take a look at our Prager University segment of today called The Truth About CO2. And this is by the former co-founder of Greenpeace.
What are two of the dirtiest words in the English language? Well, if you're concerned with global warming, as so many people are these days, the answer is obvious. The two words are carbon dioxide, or as it is known by its chemical symbol, CO2. One atom of carbon and two atoms of oxygen. If we pump much more of it into the atmosphere, the argument goes, we're going to alter the climate, catastrophically. According to the Intergovernmental Panel on Climate Change, the IPCC, CO2 emissions from fossil fuels, which constitute 85% of our energy use, must be reduced to zero by 2100. If we don't save ourselves from ourselves, we're toast. That's the claim. Here's what's strange, though. All life is carbon-based, and the carbon for all that life originates from carbon dioxide in the atmosphere. All of the carbon in the fossil fuels we are burning for energy today was once in the atmosphere as carbon dioxide before it was consumed by plankton in the sea and plants on the land. Coal, oil, and natural gas are the remains of those plankton and plants that have been transformed by heat and pressure deep in the Earth's crust. In other words, fossil fuels are 100% organic and were produced with solar energy. Sounds positively green. If there were no carbon dioxide in the Earth's atmosphere, the Earth would be a dead planet, period. Talk about catastrophic climate change. Take away CO2 and you'd have it. And yet the U.S. Environmental Protection Agency has deemed this essential ingredient for life a pollutant. But how can something that makes life possible be bad? Before I deal with that question, let's get clear on our terms. It has become common to refer to the emissions from burning fossil fuels for energy as carbon emissions. That is entirely misleading. Carbon dioxide is not carbon. Carbon dioxide is a colorless, odorless, tasteless gas which is an indispensable food for all living things. Can you have too much of it? In theory, yes. That's what climate alarmists say is happening now. CO2 levels are getting too high. Are they right? Well, if we look at the big picture, we find something surprising. For most of the history of life on Earth, carbon dioxide has been present in the atmosphere at much higher levels than it is today. During the Cambrian explosion, when multicellular life first came on the scene, CO2 levels were as much as 10 times higher than they are today. From a big picture perspective, we're actually living in a low carbon dioxide era. The optimum level of CO2 for plant growth, for example, is 4 to 5 times what is currently found in our atmosphere. That's why greenhouse growers worldwide actually inject additional CO2 into their greenhouses. They want to promote plant growth. Likewise, higher CO2 levels in the global atmosphere will boost food and forest productivity. That will come in handy, since by mid-century, we will have to feed 8 to 10 billion people. In fact, we're already seeing the positive effects of increased carbon dioxide now. Satellite measurements have noted the greening of the earth as crops and forests grow due to our higher levels of CO2. It turns out that carbon dioxide are not dirty words after all. We should celebrate CO2 as the giver of life that it is. I'm Patrick Moore, co-founder of Greenpeace for Prager University.
Now, I hope you found that fascinating on the carbon cycle. We're actually going to come back to the global carbon cycle. We're going to look at it more with a chemistry look in just a little bit. But, you know, more carbon equals more opportunity for green and agriculture and forest, and there's opportunities there. And so it's important to understand and take a look at the fact that carbon dioxide is not necessarily a bad thing. With no carbon dioxide, we die. And yet, I hear from the IPCC and Al Gore and the likes of them that the goal is a 0% carbon dioxide emissions by the year 2100. That's going to kill us. But of course, they'll already be dead, so I guess it really doesn't matter to them. We're going to actually take a look now about solar jobs. Here's Congresswoman McCollum.
Energy, as well as improve our environment and our economy. The Blue-Green Alliance estimates that Minnesota could create 15,000 jobs and save more than $3.1 billion by reducing energy use in municipal buildings, universities, schools, and hospitals, and that means saving tax dollars on heat. So we need to focus on jobs, and we also need to focus on the environment, and we need to focus on reducing carbon emissions. And as we know, Minnesota wants to lead the way by also working on our homegrown energy, wind and sun. So last year, the solar industry added 51,000 jobs. That's nearly a 25% increase over 2015. 1 out of every 5 new jobs in the United States are solar jobs. Solar is only greenhouse gases. Now, solar is only the second largest U.S. energy industry, second only to oil and petroleum, and considerably larger than coal. But this sector doesn't even earn a mention in President Trump's America's First Energy.
All right, we have some data issues here. I'm actually looking at, I think, the same data set that Congresswoman McCollum is. And this is from Forbes magazine, February 7th. So the data set that she had was just before this story was printed. And it says 1 out of 50 new U.S. jobs was in the solar industry. Not 1 out of every 5. That's missing a factor of 10. That's a lot. Now, she is correct. Solar industry employment growth outpaced that of the overall U.S. economy by 17 times, as it increased by over 51,000 jobs for a total of 260,077 U.S. solar workers. So that part is correct. The number of solar jobs increased in 44 out of the 50 states in 2016. Women represent a greater proportion of the solar workforce than in previous years, rising from 18.7% in 2013 to 28% in 2016. Now, what states employ the most solar workers? I'll tell you what it isn't. It's not Minnesota. It's not Wisconsin, and it's not Michigan either. As a matter of fact, I don't even see North Dakota, South Dakota, or Iowa on the list. The Great Lakes Basin is practically non-existent from the majority of solar jobs. California employs the most solar workers, followed by Massachusetts, Texas, Nevada, and Florida. So out of the top 5 states, 4 of them are in more solar regions in the Sun Belt. Workers who install rooftop solar panels make up the largest share of employment in the sector at 137,133 jobs. Solar City, which merged with Tesla in 2016, Vivint Solar and Sunrun are the biggest residential installers. Manufacturing is a distant second with 38,121 jobs, followed by 34,400 in project development and 32,147 jobs in sales and distribution. Installation jobs grew 14% from 2015. Manufacturing jobs rose 26%. Project development popped up 53%. Sales and distribution jobs increased 32% from 2015 to 2016, according to the report. It is growing, but it's not growing quite at the 1 in every 5 jobs that Congresswoman McCollum stated that it is. Here's the other thing. I have absolutely no opposition to solar. None whatsoever, if solar can survive without government subsidies. And herein lies the question. How much is government actually paying to increase this particular sector of the economy? Now let's go back to Adam Smith in The Wealth of Nations when he claims that there is an invisible hand that impacts and corrects the economy. Well, if you're throwing in government subsidies, you are taking away the ability for that indivisible hand of market correction to actually work. And that actually hinders what its proper growth rate is. So it's not surprising to me if there's a mix of government subsidies coupled with some private sector growth. I mean, Tesla, they're working on their own solar cells, and they may make some big breakthroughs. I've heard that there may be one that's out there, and I like to see that as long as it's coming from the private sector, not the public sector. So that's what I don't know as far as the solar industry growth, but I'll tell you what it's not doing. It's not happening up here. And yes, and my producer Dallas Pearson reminds us of Solyndra, $150 million loss. That was supposed to be a big deal by the... No, it's $500 million? Okay, it's a $535 million solar project loan from the federal government into Solyndra. Dallas just looked up the figures, and that money's gone. And Solyndra went bankrupt. And that was just nothing but more than a subsidy to friends. $535 million. Don't you wish you could kind of get that kind of credit? Walk away scot-free? $535 million later? I think that's irresponsible. I think you do too. So that's the truth about solar jobs. Now let's take a look at why Congresswoman McCollum likes to serve on the Defense Committee.
Role that might, some of you, I could see some of your faces, she's on the Defense Committee. Well, there's a couple of reasons why I'm on the Defense Committee, and this is one of them. I serve on the House Defense Appropriations Subcommittee, and make no mistake, the Pentagon knows climate change is a real threat to our military readiness and our national security. Refers to it these days. Sea level rise, this is, and I'll be quoting the Navy shortly, sea level rise has the world's largest naval base in Norfolk, Virginia. They have seen more than 14 inches of sea level rise since World War I. 10 times a year, entry points connecting roads become unpassable because of coastal flooding. By the year, in the year 2100, the University of Concerned Scientists estimates flooding at these bases will occur. Flooding at these bases will occur 280 times a year. And that's where we build our nation's naval defense system. Norfolk is just one of many U.S. critical defense installations seriously vulnerable to sea rise. And you can go out and you can Google what's happening to some of our bases and outposts as we've watched the permafrost in Alaska disappear. We literally have radar stations in that they have to be moved before they fall into the ocean. So sadly, I have to say, the partisanship is so poisonous in Washington that Republicans in 2014 and 2015 even attempted to prohibit the Department of Defense from investigating to defend our defenses from climate change. Well, the Pentagon is moving forward. Rear Admiral Jonathan White, a former chairman of the Navy's Task Force on Climate Change, says there is no time to spare convincing Congress to act. And to paraphrase him, he says, by the time the seas have risen, the ice will have melted, and there will be no turning back. So there are many reasons to act on climate change, but I thought you should know what I'm doing on the Defense Subcommittee, working on climate change.
Question. Isn't the job of the Department of Defense defense? It came out of the War Department. Maybe they should rename it the War Department. Why are we spending so much time and government money using the Department of Defense to fight a full war against the weather? Now, she mentions that Pentagon knows that climate change is a threat to military readiness and national security. Well, I spent 16 and a half, almost 17 years in the United States Air Force, and not once were we ever getting ready for war against climate. We were preparing for war against our nation's enemies. We were ready to respond to the attacks on 9/11. We've done a series so far, and we will get back to the series in short order, on U.S. involvement in policy and history of the Middle East. That's what we're combating with the Department of Defense. We're combating Wahhabism. We're not combating the weather. We need to understand the weather, but we don't need to fight the weather. But yet, why are we using the Department of Defense to fight the weather when we should be fighting our enemies? We should be fighting ISIS. We should be fighting Al-Qaeda. And if need be, we should be fighting the Taliban instead of the weather. Now, the other thing is, she mentions about 14-inch sea level rise in the last 100 years in Norfolk, Virginia, and that prediction of 280 times a year of having flooding in Norfolk. There's two things. One, there might be a small little bit of sea rise, but more importantly, how much of that is the landmass actually sinking? And if you look at the two of them together, a little bit of rise and a lot of lowering, of sinking land, you might get 14 inches over 100 years. But most of that, and I've actually seen reports, most of that is actually occurring because of the landmass sinking, not because of the water quantities getting larger. And so there's a little bit of being disingenuous here in how she reports that. So now, as I mentioned before, we're going to go back and look closer at the global carbon cycle, because really this is what a lot of this stems from. We're trying to fight carbon dioxide. We're trying to fight something that gives us life. And that's what this whole Paris Agreement that President Trump pulled us out of June 1st, this is all about fighting carbon dioxide. And so I think we really need to take a closer look at how that global carbon cycle works. So let's take a look.
You and I began this journey a year ago when I introduced you to this spectacular method for understanding the world. While physics explains the mechanics of the universe and biology describes how life functions and interacts with itself, chemistry lies between. In our next course, we are excited to announce that we're going to be exploring psychology, the study of human mental functions and behavior. Chemistry has brought us great insights into even such complicated sciences as psychology, like how neurotransmitters allow us to feel anxiety and hormones give us our desires. But before we drill down into the level of your brain and bloodstream, I want to close out this course with a talk about chemistry on a global scale, certainly larger than your mind, though I'm not sure it's more complicated. It is complicated, though, and also terrifying. Let's talk about a little thing called global warming and the spiking atmospheric CO2 concentrations that are causing it. I'm sure you are aware. But awareness isn't the same thing as understanding, and if I had one final attempt to persuade you that chemistry is important, which I do, I'd tell you about the carbon cycle, which is what I'm about to do. Of all the chemistry that happens on this planet, the carbon cycle is the thing that makes Earth earthy, unique among planets that we know and understand. The early Earth's atmosphere was made up of ammonia, methane, nitrogen, and carbon carbon dioxide, among some other things, but essentially, there was no free oxygen. Many of these gases, including CO2, are what we call greenhouse gases because they absorb heat energy, thus increasing the average temperature on Earth. When plants came along with their fancy photosynthesis, they used up most of the carbon dioxide in the atmosphere. They used that carbon to make life, turning carbon dioxide into a rare commodity while producing huge amounts of oxygen to create a whole new atmosphere. These changes not only serve to open up the Earth's atmosphere, allowing huge amounts of heat to radiate back into space, they also created a huge reservoir of highly energetic organic forms of carbon that are used as fuel by living things, including us. Organic carbon, or in the language of chemists, reduced carbon, is nature's equivalent of a battery. Organisms can draw power by feeding on organic carbon compounds and then oxidizing the reduced carbon back to carbon dioxide. Lots of organisms are good at this. No organisms are as good at this as we have become. Carbon's role in the biology and physics of our planet is unparalleled. It's the main route for the transfer of energy between organisms, and it's the main way that we trap heat in our atmosphere. And that's why when we talk about global warming, we talk about carbon, carbon footprints, carbon credits, carbon loading. So let's wrap up our study of the chemical universe by going not all the way back to square one, but square 6 on the periodic table. That's right, we have a periodic table. It's designed by Thought Cafe. It's beautiful crash course chemistry periodic table. It's quite large, and you want it, and it's available for $15 at dftva.com. Since carbon is the stuff of life, one of the best ways of understanding the carbon cycle is just a whole bunch of things living and dying, and in the process, swapping carbon. Here's the 30-second version. Plants use the carbon in atmospheric CO2 to make sugars and other carbohydrates to grow and reproduce. Lots of those plants end up being eaten by other organisms, supplying them with the building blocks for other biological molecules and fuel. After being metabolized, the carbon returns to the environment in one of several different ways, ending up in the air, water, or the Earth itself. From that point, it's released naturally or is extracted by humans, in either case returning carbon dioxide to the atmosphere, and it starts all over again. So let's talk about those green plants and what exactly it is that they do. Photosynthesis is an extremely complex process, and it can happen in a couple of different ways, depending on the organism. But the main point is to take in carbon dioxide from the environment and use a process called carbon fixation to convert it to organic compounds such as sugars. It's called fixation because it takes carbon in the form of a gas, carbon dioxide, and solidifies it into solid carbon compounds. The general reaction looks like this. Note that CH2O isn't actually a thing. It's a reduced formula that stands for a simple carbohydrate, a compound that's composed of carbon and hydrogen and oxygen in a ratio of 1 to 2 to 1. In real life, there are all kinds of carbohydrates, and they're usually a lot larger, but chemists use this streamlined version to illustrate the basic reaction. And the reaction is basically the same with any hydrocarbon, but you've probably seen it written most often with glucose. In this form, we say that 6 moles of carbon dioxide plus 6 moles of water plus some light energy yields a mole of glucose plus 6 moles of oxygen. Either way, you might have noticed something important. This is a redox reaction. Carbon is reduced, going from an oxidation number of +4 to 0, and oxygen goes from -2 to 0, meaning that oxygen is oxidized. It can happen. And the carbohydrates produced by these carbon fixation reactions are the most sought after currency among Earth's living things, because organisms can use them in 2 different ways, as building material and as fuel. Some carbohydrates go through additional reactions to become even more complex, like starches, fats, proteins, nucleic acids, and all the other stuff that makes up living things. Meanwhile, other carbohydrates, the ones that are used to produce energy, go through a process called cellular respiration. Like carbon fixation, respiration is an extremely complex cluster bomb of reactions, so we typically condense it too down to a fairly simple reaction. The overall reaction for respiration is essentially the reverse of carbon fixation. A carbohydrate and some oxygen react to produce carbon dioxide, water, and energy. Again, this is most commonly written with glucose, so we'll do that here too. And like carbon fixation, it's also a redox reaction. In this case, the oxygen is reduced from an oxidation number of 0 to -2, and the carbon is oxidized from 0 to +4. That's right, the cells of living things reoxidize the reduced carbon and re-reduce the oxidized oxygen to produce all the energy that keeps living things alive. But despite the fact that these 2 reactions look like exact opposites of each other, even down to the changes in their oxidation numbers, it's important to remember that they're just summaries. The overall processes actually include lots of steps that are completely different from each other. Now, after organisms metabolize carbohydrates, the carbon can be released back into the world in several ways. For one thing, lots of carbon dioxide is released as a direct product of cellular respiration. For you and me, that happens mostly when we exhale, and that carbon dioxide dioxide can be recycled immediately by photosynthesizers. For organisms that live in water, the carbon that they release largely ends up dissolved in that water, and oceans and other surface water can also dissolve carbon dioxide directly from the air. No matter how it gets there, carbon dioxide reacts with water to form carbonic acid, a weak acid that dissociates into hydrogen and bicarbonate ions. The hydrogen ions can react with various rocks and other substances in fairly typical neutralization reactions. This results in weathering, which besides melting the faces off of statues, produces stuff that forms clays. But the carbonate ions have a whole bunch of functions, especially in marine animals, which use them to build their shells and skeletons in the form of calcium carbonate. The carbon remains trapped there until those animals die and their structures break down, which happens on huge, very slow geologic timescales. And if the conditions are just right, like in the super high pressures and temperatures in the Earth's crust, large deposits of calcium carbonate can eventually form rocks like limestone. And before you start thinking that rock equals boring, you should know that about 80% of all the carbon on the planet is locked up this way, as inorganic carbonates in the Earth's crust and mantle or lithosphere. Most of the remaining 20% is spread throughout the lithosphere too, as organic carbon from buried organic matter. So, those pools of carbon that everyone's so obsessed with, those fossil fuels that we use to power all the things, they account for only 0.006% of all the carbon on Earth. Those carbon deposits got there from the dead bodies of other organisms like plants that managed not to be eaten or have their carbon released some other way, hence the name fossil fuels, dead things that you know today as coal, petroleum, and natural gas. The general chemical reaction for combustion of those fuels is just a hydrocarbon reacting with molecular oxygen to form carbon dioxide and water vapor. For example, each mole of methane, the simplest hydrocarbon, reacts to form 1 mole of carbon dioxide. And of course, this too is a redox reaction, where carbon is oxidized all the way from -4 to +4, and oxygen is reduced from 0 to -2. Combustion is an extremely common reaction type. The only change that occurs from one example to the next is the hydrocarbon. And obviously, as larger, more complex hydrocarbons are used, the CO2 production per mole of fuel increases. What about gasoline, for example? Combustion of octane, a main ingredient in gasoline, produces 8 moles of carbon dioxide for every 1 mole of fuel used. A mole of octane is only about 0.15 liters, or 0.041 gallons, but those 8 moles of CO2 take up nearly 180 liters of space at standard pressure and temperature. This carbon dioxide is released back into the atmosphere, where it re-enters the carbon cycle. The problem with all this is that the environment can only...
All right, have you had enough yet? I know there's a lot there, a lot to jiggle your mind around and try to make sense of it all. What's a mole? What's the plus and minus thing? You know, I haven't had chemistry since probably 1987. I remember some of this, but not to that point where, you know, his script, you know, takes him. So there's a lot there that I don't know. I will admit that. I'm not a scientist. I'm a historian. But the thing is, he makes a very, very, very good point about how much carbon is in fossil fuels, because that's what we hear from the environmentalists, that we can't drive cars because it's going to bring carbon dioxide into the atmosphere, which is where it belongs. But he says 0.006% of the carbon is in fossil fuels buried under the earth. That's a minuscule proportion. Minuscule. Now, of course, I remember Al Gore and others proclaiming how much methane is in the air because of cows. Between cows belching and between them farting, there's methane, extra methane gas in the atmosphere. It's part of the carbon cycle. That's normal. That's the part of the process. There's nothing wrong. See, my whole point is that this movement that we've seen from the last 25, 30 years is all about nothing. And that's really what I've been showing in the last couple of weeks, that this is all about nothing. Now, when you actually take a look at the science behind it, and not just from the IPCC, International Panel on Climate Change, there's actually a lot more to this than what the Al Gores and Betty McCollums of the world will actually have you believe. So that being said, there's a little bit of a crash course in chemistry, stuff that I completely forgot for many, many years. That was actually a crash course for me. But that doesn't change the fact that they still push the same stale narrative. Now let's take a look at the hockey stick. This comes from John P. Abraham. Dr. John P. Abraham, he is a electrical engineer at University of St. Thomas. He has a Bachelor of Science degree in Mechanical Engineering from the University of Minnesota in 1997, a Master's in Science, MS degree in Mechanical Engineering from the University of Minnesota in 1999, and a PhD in Mechanical Engineering from the University of Minnesota in 2002. Notice he's a mechanical engineer, folks. Now let's see what he says at McCollum's Town Hall meeting.
This is a very famous graph called the Keeling curve. This shows carbon dioxide measurements. They've been taken since 1957. Famous curve. It may disappear because the funding to take these measurements is under threat. But what we've seen is an increase of carbon dioxide, which is one of the most important greenhouse gases, of about 40%. There's no doubt that greenhouse gases are going up. So what? So what? Greenhouse gases are going up. Well, what's happening with the temperature? This is another graph, a very famous graph, comes out every year, comes out in January. I'm very afraid this is the last time you see it because the vote was passed in the House last week to instruct NASA to defund NASA's climate budget. So this graph comes from NASA, maybe the last time you saw it. That's 2016. Here are the hottest years on record in order going back to 1880. Random, natural, I'll let us all be our individual judges. This is what we've seen for the last 1,000 years. That's the next century. So, but what we want to know is not what an abstract temperature is going to do. We want to know how is it going to impact me. Well,
and this is the problem with extrapolation because this is also NASA data. Notice that that particular data set came from Goddard. Well, this particular data set also comes from, I believe, NASA Goddard. But take a look. This is the Greenland ice core. Now, notice the same type of graph where it's curving upwards. And it looks like we're going to extrapolate, but take a look when we look a little closer here on what that means. It still goes up and down. It just happens to be smaller parameters. That does not look like we're going up. That does look like it's heading in the opposite direction. You know, and this is the ice core temperature anomaly data. And then don't forget about the interglacial temperature for the last 10,000 years. The Minoan warming. Tell me where there was SUVs back then. Roman warming, I mean the Roman Empire, and then we had the medieval warming. And look at, on the far right, little ice age, and then that little tiny red spot of spiking up is where we're at now, and that's what Betty McCollum and Al Gore are concerned about. It doesn't look to me like there's really anything that we should really be worrying about when you actually take a look at it on a longer than an 1880 to 2000 scale. So that's kind of where we're sitting at with the ability to manipulate data sets and give you only a portion of the problem to make you an alarmist. Now, of course, they'll call me a denier. Well, hey, I'll take that with a badge of honor. I am a climate denier because I believe that the climate is cyclical. Now, 97% of climate scientists agree, that there is global warming. Yes, and if I was a scientist, I might actually agree with that. I will disagree with the man's cause of global warming actually amounting to anything in light of the global carbon cycle. But we're also going to take a look, before we end the show today, with another thing that they bring up, and that's Antarctica and the Arctic Circle, and how we're so concerned about the ice sheets melting. Well, let's take a closer look here as to, again, let's take a look at Betty McCollum's expert, Dr. Abram.
Ice around 1980, it was the equivalent of the U.S. minus Arizona. That's how much we lost by 2005. That's how much we lost by 2007, and since then we've lost Texas. So this puts it into perspective, the equivalent area of the U.S. We've lost about 70% by volume of the summer ice winter. That tells you something's happening. This is a lake on Greenland. Greenland's actually an ice sheet. If you look in the back, you can see an ice sheet. And there's a motorboat on the way. Let's go to the South Pole briefly. And again, I know I'm going through this stuff quick. Write to me if you want these slides. The Larsen B ice shelf is a typical ice shelf on the South Pole. Here's a series of satellite images taken over the course of a month and a half. Collapsed into the ocean. How much was that? There's Rhode Island superimposed on that ice shelf. An ice shelf, this shocked scientists. How could an ice shelf that's been around for 8,000 years collapse in one? I'm going to show you some before and after pictures of glaciers, some of them in the U.S. The cameras are always from the same location, so you can see the effect. And some are in, this one is in Europe. So we're seeing ice being lost, we're seeing changes of drought, changes of flooding patterns. So what does this mean to us?
Cameras are always from the same location to show you the same effect. And if I actually stood on the St. Paul High Bridge and took a photo of the Mississippi River in February and stood in that same location on June 16th, I have a feeling we would see dramatically different landscapes. So is that proof of global warming, or is that just proof that summer is here? That just shows how disingenuous this whole thing is. I mean, oh, we'll show you a photo from 1909 and a photo from 2014, but I would actually like to see photos on the same date from the same angle. And let's see those photos over time. They're not going to show you that. Now, we're talking about all of this ice sheet from Antarctica. The Antarctic sea ice is melting. We're losing this shelf and that shelf, and it's a catastrophe. However, NASA, on their website, September 19th, 2014, Antarctica and the Arctic are two different environments. The former is a continent surrounded by an ocean. The latter is an ocean enclosed by land. As a result, sea ice behaves very differently in the two regions. While the Antarctic sea ice yearly wintertime maximum extent hit record highs from 2012 to 2014 before returning to average levels in 2015, both the Arctic wintertime maximum and its summertime minimum extent have been in a sharp decline over the past decades. Studies show that globally, decreases in Arctic sea ice far exceeded the increases in Antarctic sea ice. However, September 19th, sea ice surrounding Antarctica reached a new record high extent this year, covering more of the southern oceans than it has since scientists began a long-term satellite record to map sea ice extent in the late 1970s. We're only going back 30 to 40 years in data here. Notice that the charts are all pointing out, 1880 to 2000. And it's shown you the 10,000-year chart of, the warming in the Greenland ice data. But here in Antarctica, the only thing we're showing you is from the last 30 to 40 years. There's not enough data there to be able to tell you whether or not this is a normal pattern. But yet, Dr. Abram, which Congresswoman Betty McCollum proclaims a mechanical engineer is the expert, ends up giving us something that's only showing the sea ice less than 20 million square kilometers that it was in 1979. Yet, forgets to mention the fact that Antarctic sea ice is at a maximum for the last 35 years. Now, when we look back at the glaciers, let's take a look at Greenland. There was a situation in 1944 when the Lost Squadron had flown their P-38 Lightnings onto the Greenland ice shelf. And that was discovered 50 years later, as we're now in the 75th anniversary of World War II. 50 years later, so 25 years ago, they were discovered under 268 feet of ice. Over 50 years, there's 268 feet of ice. That does not sound like warming to me. Let's take a look about the Glacier Girl.
That's number which one? Are we skipping the NASA?
It should be Hunt for Lost Squadron. Well, I guess we will not be showing you the Glacier Girl. Anyhow, other than to mention the fact that a P-38 was taken from the, he found it,
on the Arctic
and
ice
here's the video.
lies a lost treasure worth millions.
8 fighter planes crash land here in 1942.
These airplanes are never seen again.
For 50 years, the planes await someone who can solve their mystery
Nobody knew what was going to happen.
and survive the brutal cold of the Greenland ice cap.
With 70-mile-an-hour winds, I couldn't see 3 feet in front of me.
Many will take on the extreme challenge,
The whole thing is incredibly difficult.
the extreme risks,
I thought, I'm going to die.
the extreme technology.
It was like a quest. I've got to find them, get to them, then bring them up.
But few will survive the clash of egos and the battle for control.
I went up there to see my money go down an ice hole.
He says that he came in and took over the expedition. It's just a damn lie.
Their quest will become a multi-million-dollar obsession to uncover one of the greatest treasures in aviation history.
Now, we had just shown you a trailer for a documentary based upon that particular story with the finding of Glacier Girl, but I felt that was just enough to, let you know that there's 268 feet of ice that had built up in Greenland over 50 years since the aircraft went down and to when it was discovered. And you can actually see Glacier Girl as she makes the air show circuits around the country. And I don't know when she'll be in this area again, but perhaps if you go off to Oshkosh for the EAA's annual shindig over there, you might be able to get a glimpse of her. It's a fascinating story. But back to the climate. Here we're talking about the ice sheets and how ice is melting in the Arctic and how it's, expanding in the Antarctic. Could that be because that's the way it was intended at creation? And here is what NASA has to say about the Arctic and Antarctic being the polar opposites.
The Arctic and the Antarctic play the role of kind of like an air conditioner for the Earth systems. They're cold, they have a lot of ice, they reflect a lot of the solar energy, so they stay colder than they otherwise would. They're more sensitive to climate change, and therefore they're the regions that we see the biggest effects of climate change so far and the biggest effects of warming. They're kind of the canary in a coal mine of global warming.
This year's Arctic sea ice minimum is in about the top 10 of the lowest that we've seen in the last 3.5 decades. As the global temperature has increased, the temperatures in the Arctic, especially in the past decade, have increased by about 2 to 3 times the global average. And so what's happening is temperatures increase, ice melts.
Well, this year in the Antarctic, we've seen a pretty spectacular maximum extent. The Antarctic sea ice has expanded beyond anything we'd seen before and set a new record. The increase that we're seeing in the Antarctic extent is a little bit of a mystery. We're seeing overall temperatures warming around the globe, so you would expect to see ice loss. Some people have looked at the Antarctic increasing trend and used that to suggest that global warming isn't happening, or that the increase in the Antarctic is offsetting the decrease in the Arctic. And that's simply not true. If you look at just simply the magnitudes of the changes we're seeing, in the wintertime, the Arctic is decreasing about twice as fast as what the Antarctic is increasing. It's important to look at the relationship between the Arctic and the Antarctic because studying those gives us an indication of what changes we're going to see around the rest of the globe in the future.
There's one thing that he missed in his last analysis, and that is the size of the Arctic versus the size of the Antarctic, because the Arctic is surrounded by the tundra masses with the tundra on the land masses. It is actually a smaller area. So if there's a rapid decrease in the Arctic but a slower increase in the Antarctic, if you actually take a look at the amount of square kilometers between the two, you will probably find that there's really not much of a difference. They are the polar opposites. So I have a feeling that when the ice sheet in Antarctica recedes, that we'll actually get more polar ice. I mean, that's kind of how the Earth breathes. That's what I understand. And we played, I think it was either last week or the week before, we played a video where Al Gore admits that this is how the Earth breathes. And he shows the Arctic Circle, and ice goes in, and it retreats, and it recedes, and it contracts and expands, contracts and expands. More ice, less ice, more ice, less ice. That's the way it is. It's a normal cycle. Why are we worried about something that happens normally that we're not going to stop? Now, there is another cause. There is probably another cause, and this actually has to deal with why we actually have the aurora borealis. This is probably the most interesting part of the show. If you've been bored so far, hey, this is going to be fascinating, at least the graphic at the very end of this next clip. Because everything here that they've discussed so far makes an assumption that we're only dealing with what's happening within the Earth. We're only looking at what's happening underneath the atmosphere. But like we had mentioned last week with interplanetary climate change and interplanetary warming trends, how does the sun and the solar cycle impact all of this? Especially at the poles, because we have something called a magnetosphere. The magnetosphere is what protects us from the harmful nature of the sun's rays. And so we are going to take a look at space weather and the Earth's aurora from a NASA video, and hope that you can understand a little bit more as to how the sun impacts the Earth, and then take a close look at where the radiation comes in, because you're going to notice it is at the poles.
On Arctic nights, the aurora often flames across the winter sky. What is it, and where does it come from? This is where the tale of the aurora starts, on the Sun, a star of average size among billions of other stars in our Milky Way. The Sun acts as an enormous power plant. The energy is created deep inside the core of the Sun. Here the temperature is over 14 million degrees, and the pressure so enormous that hydrogen atoms are squeezed together into another element, helium. This nuclear reaction releases energy. The light radiates outward from the core of the Sun. In the outer layers, the heat moves to the surface in huge eddies called convection cells. These electrical currents of charged gas create magnetic fields inside the Sun. In some places, strong magnetic fields push their way up through the surface. They slow down the eddies of hot gas. The surface cools, and darker sunspots appear. The electrically charged gas is called plasma. The plasma drags the magnetic field further outwards. The magnetic field stretches and twists like a rubber band, and then the rubber band breaks. Several billion tons of plasma is hurled out from the Sun. This is called a solar storm. The solar storm can reach speeds over 8 million kilometers an hour. After 6 hours, it blows past the planet Mercury. After 12 hours, the planet Venus. And after 18 hours, the solar storm reaches Earth. When the solar storm reaches our planet, something strange happens. An invisible shield, the Earth's magnetic field, deflects the storm. The magnetic fields couple together and create a funnel where the gas streams down on the daylight side of the pole. This is the daylight aurora. The magnetic fields stretch further back and couple together. The magnetic rubber band breaks, and gas from the solar storm streams along the magnetic lines towards the poles on the night side. This is the nighttime aurora.
And there you have it. We have all this concern about the Arctic and Antarctic circles and the ice mass, and we don't even talk about the Earth's magnetic field, and we don't talk about space weather. We don't talk about coronal holes and solar wind. We don't talk about solar flares. We don't talk about coronal mass ejections. We don't talk about how the Earth actually receives its radiation from the sun. Yet that is a very big part of this whole discussion, or it should be a big part of this whole discussion. And so we will no doubt be continuing at some point in the future a discussion about space weather, which we kind of started last week. But with that, we are going to go on to our music segment. We're going to look at the Bare Naked Ladies' Snowman. So for Dallas Pearson producer, I'm your host, Jeff Williams. You are watching North Star Oasis, and reminding you that as we watch the snow globe for Snowman, there's only 191 shopping days left until Christmas. So thanks for watching. We'll see you next week.
Made of snow, I don't know how I fit in. To and fro, people go, I stand and grin. Way to go, even though I can't begin. Made of snow, I don't know how I fit in. Ever cold, love untold, I don't belong. Having holes, so we're told, I think they're wrong. Heart of gold, growing old, just like the song. Ever cold, love untold, I don't belong. Button eyes, lullabies, I melt away. Criticized, compromised, white turns to gray. I'm paralyzed, otherwise I'd leave today. Button eyes, lullabies.